Hi, I'm back for the last time. So this is the last lecture of this 10th lecture series. Today I'm going to start talking about topological insulators. Since we have already discussed graphene in terms of this Dirac fermions, so it is natural for us to extend that discussion for this newly discovered phase of topological insulators. So let me get started here. So in this lecture, mostly I'm going to talk about effects of spin on transport of electrons in solids. So that's basically covering topological insulators. Before we get started, what is the effect of spin? So actually spin has been the reason why we have this interest in effects like Mott insulators, so Rush-Bar effect, and some novel superconductivity, and mostly the new quantum information and quantum computation. So they all make use of electron spin. So we already have talked about spin on the magnetism. So here we are going to mostly talk about some relativistic effects and the influence of spin on various properties of these materials. So this topological insulators is a new phase of these materials. So actually, important thing is if you take some bulk materials, so some materials, they are interior. The bulk is very insulating, but they have electrically conducting at the surfaces or at the exterior of the material. So it's due to something called this surface states that makes something called this conducting edge states. So at the moment, most of this edge conduction or surface states make use of spin orbit interactions, but there have been some other phenomena associated with these edge states, but most of the concentration has been based on spin orbit interaction. Actually, because of that edge states, usually, so what we have in most material, the time reversal symmetry, so that is be broken. So because of this spin orbit interaction, so generally these topological insulators are related to time reversal symmetry breaking. So we'll talk about that one a little later. So actually, this is not real any hypothetical situation. So people have observed these topological properties in certain materials. So using something called this angle resolved photoemission spectroscopy experiments, something called the ARPS. So before we get started, let me talk a little bit about types of order. So order has been the cornerstone in many phenomena, right? So much of condensed matter is about how different kind of order coming from interaction between their constituents, so of what they are made of, like in electron-electron interactions or electron-phonon interactions, or how these constituents interact with the outside environment. So these all have some kind of order. So until like 1980, these ordered phases could be understood as something called symmetry break-in phenomena. So here you can see some highly crystalline diamond or some ordered other atomic configurations. So until like late 1980s, so these ordered phases people understood as a phenomena of symmetry breaking. Actually, when some material is cooled to very low temperatures, so that we see some emergence of some ordered state when there is this spontaneous loss of one of the symmetries. So usually present at higher temperatures. So when you really go to really low temperatures, so one of these symmetry will be lost. So that's more like a symmetry break-in situation. So that symmetry break-in will result in some new order. So some of the examples are, if you look at simple crystals, they break the translation and rotational symmetries that when you have in the free space. So if you look at the free space, so when you at the boundary of the material with the free space, right? So when you go into the crystals, so there's some breaking of the translational and rotational symmetry. That's why we have some new crystalline phase. So that higher order we had in the free space, now we have some loss symmetry inside the crystals. If you take a liquid crystal, so this liquid crystal devices, I think their symmetry is broken due to rotational symmetry, actually, not the translational symmetry. So that's why liquid crystals are special compared to crystals. In the crystals, we are talking about the break-in of translational and rotational symmetries present in free space. But in the liquid crystals, we are talking about break-in of rotational symmetry, not the translation symmetry. If you look at the magnets, so actually in magnets, you have the break-in of time reversal symmetry. Also, in addition to the rotational symmetry in the spin space. So if you look at the superfluids like helium-3 or helium-4, so it's more like some internal symmetry related to some quantum mechanics. We know how these fermionic or bosonic pairs of helium-3 or helium-4 states, so they have some breaking of internal symmetry related to quantum mechanics. So then if you look at the types of order, so we know material when they are at very high temperatures, so typically entropy dominates and it leads to disordered state. We know your entropy is always increasing, right? So your ds is always greater than or equal to 0. So if you talk about high temperatures, since the entropy dominates, so it always leads to disordered states, right? So because entropy means you are favoring disordered states. But if you look at the low temperatures, it's energy is the dominant phenomenon, right? So not the entropy. So that means they lead to more ordered states. So you can see the difference between high temperature causing disordered states because it's dominated by entropy. At low temperatures, since it is dominated by energy, so they favors ordered states. If you look at these two examples here, you can see this one. In the left side, we see standard phase transition of liquid to a gas. So we can think even in terms of water boiling, right? So you make liquid and gas. So, but we know there's something called the critical point, right? Some critical temperature. Above that critical temperature, we have this supercritical phase, right? So then if you look at these two phases, so between liquid and gas, if you look at the density, liquid density minus gas density, actually they follow this kind of scaling relationship. We have this Tc is your critical temperature. Here, this is more like the supercritical temperature, right? So minus T over Tc times some exponent. So same thing if you look at the Ising model, right? For ferromagnets, Ising model is this interacting two spins, right? So if you look at in simple Ising model in one dimension, so it's a uniaxial ferromagnet. So we know on the if you look at the magnetic field due to that spin, so as a function of temperature, we find this magnetization has some critical temperature. This is for a ferromagnets, is related to the Curie temperature. And the ferromagnetism is related to the Niels temperature, right? That's the critical temperature here. So again, if you look at this magnetization, the difference between these two, just like liquid and gas densities, you have magnetization due to spin up and magnetization due to spin down. That difference also related to similar scaling behavior. So this Tc again is the critical temperature, like Curie temperature. So theory shows this beta is like 0.3. So actually experimentally people have measured that to be very close to that theoretical prediction. So actually this is a universality at these continuous phase transitions, right? So they both are continuous phase transitions, so they have some universality. So now if you look at these types of order, so in 1980, people actually found there can be some ordered phases beyond symmetry break-in. So you don't have to have symmetry break-in to have a new ordered phase. So actually, the very first observation of this ordered phase, other than symmetry break-in, not resulting from symmetry break-in, is actually the discovery of this quantum Hall effect. So we already discussed about that many times, right? If you have this longitudinal resistivity rho xx and transverse Hall resistivity rho xy, we already showed. So classically we have this linear B relationship, and also the rho xx is mostly the true conductivity. But if you go to high magnetic field, they show this oscillations. So whenever you have the zero value of this rho xx, you see the plateaus of this the whole resistance, right? So then also they found this rho xy, or if you take the inverse of that, whole conductivity goes like E squared over H times N. So this actually, this is a new type of order. So there's a quantum Hall state. So that not resulting from this usual phases resulting from symmetry breaking. So but thing is, what type of order causes this quantization? That's the question. So this is a new kind of phase arising due to not due to the symmetry breaking, right? So the question is what type of order? So we know that phase transition, but what causes this new phase? So actually, if you look at this one, this new order we call is a topological order. So this we need to understand what type of order causes this precise quantization in this integer quantum Hall effect. So we introduce something called this topological invariant. So in a topologically ordered phase, that's what we are looking at, these things like quantum Hall effect. So there should be some response functions. So given by topological invariant. Topological invariant means, so if you deform the system, so it will be invariant under that deformation. It's more like, we'll talk about that one. It's more like this the coffee mug can be topologically transformed into a donut by introducing continuous deformation. So then actually that phase we later introduced into this something called, we introduced, remember, topological material. You have insulate in bulk, and so some conducting edge or surface states, like I talked before. So this is what we talk about, this topological invariant. That does not change under continuous deformation. Like I explained to you before, if you start from this coffee mug here, if you gradually deform this one, so you can see it's becoming deformed and little bit more deformed, little bit more deformed. Eventually, it can become donut shape, right? So this is, we don't do anything, it's continuously we deform that, so it ends up with this donut. So then these two structures we call, they are topologically invariant. Okay, so when we talk about this Hall effect as a new order, right? So we already talk about this Hall effect coming from this simple. Classically, if you have current electron moving, if we apply magnetic field, so we have transverse Hall voltage. So that's where we have the classical Hall effect. But in 1980s, they discovered the quantum Hall effect, right? That's where we saw these plateaus and peaks. So then later in 2005, so they found this, we discussed about this one, this something called the half integer quantum Hall effect. So this is typically we have this expression. So but now when you have this something called pseudo spin and additional half coming from the spin of the pseudo spin, so you get this kind of half integer quantum Hall effect. These all are new order of the state. So that is not resulting from standard symmetry breaking phenomena. So then also we know if you look at something in a material, if I apply some electric field, what will happen? So the usually electrons are moving in the direction of that electric field, right? So now if I apply a magnetic field, we have a Lorentz force, so then it will make this kind of spiral motion. But if you increase that magnetic field more and more, so then this become this we call the cyclotron motion. So this electrons will only move about this circle. So if your magnetic field is larger than that, the radius of the that path becomes small, right? So this means these electrons, they don't really go from one end to another end. They are more like localized here, right? So that means this gives you something called the insulating behavior, because electrons don't move from one end to other end. So but at the edges, so they kind of skip these orbitals. So it make a little bit, let's talk about that one. That means they can actually, electron can move along these edges. So that's where you get the edge states. So then actually later Haldane, so he talked about, because we know that quantum Hall effect all coming from this Landau levels, right? So when you have magnetic field, your energies are going to be split into this equally spaced energy levels called the given by H cross this omega c, that's the cyclotron frequency given by EB over M. So, but in 1988, Haldane, so he showed, so you can even see the integer quantum Hall effect even without this Landau level splitting. So what he found was, if you have like zero magnetic field without any magnetic field, we have this for graphene, we have this Dirac cone, right? But if you have some periodic magnetic field, so we are talking about not static magnetic field. If you have a periodic magnetic field, then there will be some charging happening in the graphene. So that will cause some splitting of your bands at the this K points. So this is usually at K point you have these two touching each other, right? That's the Dirac point. But due to this periodic magnetic field, you have some opening, so that gives you some band gap. So like here, showing here. So that is also new kind of phase, right, or new order. So actually, if you nowadays people have come up with various type of Hall effects. So the first one is what we usually talk about, right? Classical situation. If you apply a magnetic field, then the electron will have a Hall field proportional to magnetic field. So, and also your transverse rho xx is constant given by the Drude conductivity. But at high magnetic fields and low temperatures, they find this quantum Hall effect, right? So that is, you have this oscillations in your rho xx and plateaus in your rho xy. That so then actually later they found you don't have to have a really strong magnetic field. So with this spin orbit coupling, so you can have this something called the spin Hall effect. So then they discovered even stronger one spin Hall effect with some quantum aspect. So that we call the quantum spin Hall effect. So then also there's something called the anomalous Hall effect. That's because if we have some ferromagnetic material, we have this natural magnetization. Because of that, you can have some Hall effect. So that's called the anomalous Hall effect. These are all things people have already observed. So typically, let me show you the standard Hall effect. You need to have a magnetic field. Then these electrons, usually they go like that, and then they turn and make in this Hall field, right? That's what usually we see for metals and due to the Lorentz force. But here you will see because of that magnetic field, your time reversal symmetry is broken. So also there's no spin current because it's you don't have any, because it's mostly electrical current, right? We are talking about because electrons are moving. So then the spin Hall effect, there is no external magnetic field. So it's mostly due to this spin orbit coupling. So this one path is actually influenced by the other spin. So that means it's mostly there's without external electric field. So this is happening from this spin orbit coupling materials. So it's all coming from the spin orbit. So there's no Lorentz force. But since they have both spin up, spin down, so you will see they have the time reversal symmetry. So there's no Hall voltage because we don't have any magnetic field to have the Lorentz force, right? So then this is what the anomalous Hall effect. So this is if you have a ferromagnetic material, you have that natural magnetization. So because of that, still we don't apply external magnetic field. So now in this case, you have due to the ferromagnets, right? So you have spin orbit coupling, and also there's some imbalance because of the magnetization. You can have more spin up or more spin down. Because of that, there's some imbalance of the spin contributions from up and down. So that means there is no time reversal here. So time reversal symmetry is broken in this case. And so then if you look at how things are going, like we discussed, Hall effect to quantum Hall effect, then spin Hall effect to quantum spin Hall effect, anomalous Hall effect to quantum anomalous Hall effect. You can say they all are kind of interrelated. So now let's talk a little bit about this topological invariant. Remember, topological invariance is something under deformation, so it can go from one order to another order state. So before we introduce that one, there are a few things we can understand. Most of here these three structures. So this one in the middle, they have zero Gaussian curvature. So because you can see it's R1 and R2 like infinite, right? So that means you have Gaussian curvature 0. But if you look at the one in the left, they have Gaussian curvature negative. So because it has this structure, so the one in the right, that's more like the sphere, they have a Gaussian curvature positive. The K is positive for that one. So that is open surfaces, right? So now if you look at the closed surfaces like this one, and this is also a closed surface. So if you want to find this the curvature, we have to look at, like I said, we have to look at the integral of this some geometrical quantity. So if you take the integral of this geometrical curvature with its area, so over the entire surface, so they found this actually, that integral is actually quantized. So the area integral of the curvature is K, over the whole surface is quantized by this number X. So it's all in like X can be some quantized numbers, right? So this is called the Gauss-Bonnet theorem. So then they found this number is actually 2 minus 2G. So this G is called the genus. So this G is 0 for sphere, 1 for torus, and so if you have n-hole toruses, so if you have different, then that depends. So it's how many this toruses in that. So here we have 1 torus, right? So that in this case, any 1 for that one, that integral. So if you have n number of holes, so that number will be n. Okay. So next, I like to talk a little bit about the Rush-Bar effect. So Rush-Bar effect is very similar to if you have some electron in a electric field. So we know we have associated electric potential, right? So it's given by negative grad V potential gradient. But just imagine if you have a spin orbit coupling. So now if you have a spin orbit coupling, the electron will have the energy given by mu dot B, right? Mu is the magnetic moment here times B. But here we are talking about that B not coming from the any external magnetic field, coming due to the motion of that electron. So when the electron is moving in electric field, so that produces magnetic field. So relativistic magnetic field given by V cross E divided by C squared. So this is something you learn in the electromagnetic theory. So now you can plug in that B, this value. So then if you solve that one, you get your mu is given by, because mu is given by, remember, GS mu B times S, right? So that now if you plug in here, so that this becomes, so this is a value for S. So you have mu B, so then mu is given by, so this is definition of your magnetic moment, right? GS mu B. So this is spin magnetic moment, S divided by H cross. We did this one under magnetism. So now if you plug in this B and mu here, you get this expression, right? So mu, you get S value. So then E, we need to substitute this minus grad V. So then if you manipulate this one in terms of the polymer term, so that is basically right in this one in this way, because sigma, we know sigma value, sigma x, sigma y, sigma c, remember 1, 0, 0, 1, or minus I, so for sigma y. So if you write this way, you can easily write your this Hamiltonian like this. So one thing what people found is for graphene, so this spin orbit interaction term is pretty weak. So we don't see much this topological properties coming from graphene, because if you take graphene, so remember you have this electronic band structure. So this is your K and K prime points, right? So then we have electronic band structure like this. So at K we know the energy changes linearly, right, at the Dirac points, because at these both K and K prime we have the same energy. Because this one and this one, we call these 2 points, these are we call the valleys. Valleys are the points where you have the same energies. So then, like before, we can write this one in terms of your Hamiltonian. So remember, relativistic case, this is your Hamiltonian given by psi. Same thing you can write for the other valley, so the other Dirac point like that. So like before, we can separate this one in terms of the spin matrices. So this is your Schrödinger equation. So then actually somebody can easily write this one in terms of this spin, the polymatrix term, and also the valley matrix term. So basically this is, you are separating the spin, the polymatrix term for because valley matrix term gives you the c direction component. So then you can write your H0 as, so this is your you're operating on this quantity here. So psi, this is your conjugate of your wave function, and this is the wave function. So if you then this is your spin orbit contribution of your Hamiltonian can be written this way. So this again you can see delta SO times your this psi plus sigma c. This basically coming from SC term, right? So that is the c direction spin term. So that gives you the energy. Remember, psi h times psi in the c component will give you that quantized value, right, in the Schrödinger equation. So then we can write this Rashba term so as, so this is some constant times is psi plus, so you can write basically this time minus sigma y sx. So we can easily manipulate this spin orbit coupling in terms of polymatrices like we discussed in the case of graphene. So from this one actually they calculated, so what kind of gap is formed using this. This is the Hamiltonian, right? That's what we wrote as different terms, right? Sigma dot p, then E is given by this equation. So like we said, this S coming from spin, tau coming from valley, and sigma coming from that pseudo spin, right? So that is sublattices. So we can see there's a small gap. So they calculated that gap given here. So, but this gap is pretty small when you this lambda r value. That's the coefficient in front of that spin orbit Hamiltonian. If this value is greater than HCO, this gap is pretty much vanishes. You don't have big gap, but otherwise you have gap of this 2 times this delta SO minus that constant term here. So important thing is that for graphene, this spin orbit effect is really small, very hard to observe. So that's why I think graphene doesn't have this topological effect. So that's why we need to talk about some other materials. They have good topological insulator properties. Actually, first material they have seen the topological properties is bismuth antimonide. So in this one, they have seen the inside the bismuth antimony crystals, so they are very insulating, but they see conduction at the surface. So the small coming from the surface states, not by the edge states. So because these are three-dimensional material, so we'll talk about that one. If you have three-dimensional topological insulators, we are talking about surface states. But if you go to two-dimensional materials, mostly we are talking about the edge states. So here, the one, that's what I was talking about. This is the three-dimensional topological insulators. Inside the material, there is no conduction because they are all confined the cyclotron orbitals. But on the surface, you will see this conduction. So these are due to this spin orbit interaction. You have spin up and spin down. So you can, these are surface conduction. So but they moving in opposite direction because you have spin up, spin down motion. But this conduction is mostly due to the surface states. But in two-dimensional, like in the graphene kind of situation, we know we don't have this strong spin orbit interaction, but still you can have this edge in the case of graphene, right? So we didn't have that strong spin orbit coupling, but the standard two-dimensional topological insulators that people have already observed, so they show conduction at this. These are called the edge state. So edge state is more like that. We have these skipping orbitals. You have these two the path. So that the one with the red is with the one has spin up, and blue one is with spin down. So these are all the coming from the edge states. So if you look at typical this bismuth telluride or bismuth antimonide, so this if you take the situation going from, so this is like bismuth no arsenic, is all bismuth. So this is like all antimony. So there's no actually this is bismuth antimonide. Yes, yeah. So you have bismuth and antimony. So this is all bismuth, no antimony. This is all antimony, no bismuth. So this is some composition in between, like bismuth to antimonies. You have antimony in like 0.2. So then so you can see if you go from here. So if you look at in the brilliant zone directions, so it's going from L point to K point. So at the L point, you have these two the band edges, LA and LS. So if you, this is for pure bismuth, but if you go to pure antimony, you will see these two bands are inverted. So you can see this LA becomes LA, inverted. So, but in between you will see some intermediate state, still it is inverted. So this causes some this topological invariant properties. So here we are talking about real space properties, right? Like here, so we have this one going up and other going down. It's more like a spin motion, right? But if you look at in the K space, we are talking about this like relativistic particle. So you have this upper Dirac cone and the lower Dirac cone. So we are talking about if it is going like this or like this, we are talking about electrons moving on the this Dirac cone surface this way or going on this way. You have to understand real space versus K space phenomena. So actually these topological insulators have a lot of promises because these states are very robust to perturbation. So that means they are very stable, right? So if you use these for quantum computations, these states are very good stable qubits, right? In qubits, we need to have these two states, so very stable states, right? That's why we can have something called the quantum entanglement or like that, right? So these topological states are very robust for perturbations. They are good stable qubits for quantum computations. Also, since these are mostly due to the spin current, right? So not due to the electron current. So they have very low dissipation. So that means these are good for spintronics. So then also people have found these topological states can lead to new superconductivity. So some new phenomena of new mechanism of superconductivity. So they have a lot of promise. So this is actually the first, we call the first topological insulator people have discovered. This is coming from this cadmium mercury telluride. So you have this cadmium telluride sandwich, the mercury telluride sandwich between two cadmium telluride layers. It's like superlattice structure here, right? So then again, you can think this one as this band inversion, right? So you have this band at L point and in the brilliant zone. So you can see when you change the distance between these two, or the thickness of the mercury telluride, they find that band inversion. So you can see this becomes here, P becomes here. So what they find is ideally they are this like real insulators, but due to this band inversion, you will see some surface states. So that will make this is becoming like there's no gap here. So it's becoming more like this Dirac-Kohn kind of situation. Actually, that's what they found in this situation. When you look at the resistance as a function of gate voltage, they found very large resistance, like 10 to the power 7, because they have very large band gap. But when you have this inverted situation, so then this the resistance decrease by several orders of magnitudes, because now you have conduction due to this the band overlapping, right? So because we have this due to surface states, you have some conduction happening here. You can see this is now decreasing in the order of actually this is E squared over H order of resistance, right? So this is this is resistance H over E squared. So you can see this is the situation when it is in normal state. So that is very large resistance. So because of this large band gap, but when you have the inverted situation, so it goes by at least 3 orders of magnitudes, right? So it becoming like in conductance units, this is like 2 E squared over H, this is like 3 squared over H. This is mostly due to this band overlap. That's the first kind of topological insulator, is cadmium mercury telluride. So then they found something called the second generation topological insulators coming from this bismuth selenide, antimony telluride, bismuth telluride. This is more like group 5 and this chalcogenide groups, right? So these ones, they found similar things. It's all coming from this Dirac-Kohn situation, right? So you find your density of states has this kind of plateaus here. So they have this spin orbit coupling derived this topological insulators due to spin orbit coupling. So then if you look at actually this simple mechanism, just talk about what really are the topological insulators. If you take real band insulators, what you have is you have valence band, you have the conduction band, you have the band gap. For typical insulators, this is huge band gap, right? So that means there's no motion of electrons. So it is more like this localized states here, right? So electrons cannot move from one end to other end because they are localized in this large cyclotron orbitals. But if you have a magnetic field, what happens is it will make some this edge states. So because these orbitals, if they don't complete the entire orbit, so they can just make half of the orbit, right? We call the skipping orbit. So that means electron can really move along that direction. So that means actually it's a unidirection, right? You will have conduction at the edges in one direction. So that means you are more like connecting. So due to edge states, you will have some overlap in here, right? So these 2 points will be connected. But if you have the spin orbit interaction, so that means you will have spin up and spin down. They go in both directions, right? It's more like one going this way and other one going other direction due to this spin up and down. That means you can have both connected, right? This is only due to one unidirectional motion. Now you have both direction. You will have this like this. So this is where you get the very high conductivity, because now you have no band gap. You have this conductance coming from these surface states. So here's another picture. You can go from standard band structure. So now if you look at some this we call the band twisting model. So if you have some band, this is untwisted one. So you have this filled valence band and empty conduction band is all filled. So now if you have some spin orbit coupling, so this band is getting a little bit twisted. So then you have this one directional conduction situation. Now if you twist it more like this one, then you have both ends. So this becoming more conducting topological state. So then this we already talk about this coming from the Rishba effect, right? So you have E coming from this delta V, then we have P dot S. So then we know inside your delta V is 0. So but then you only have this edge states, right? So this is a simple two-dimensional case. Even if you have a thin film, it's the same situation. So when you don't have at the edges, your delta V is non-zero, then you have these surface states. Inside, your delta V is 0. So this is, we already talk about the Rishba effect. So this is another the summary of what we talked about, these topological insulators. So here's another summary of that one, insulating state, but in the quantum Hall state, you have the something called the Landau levels. So that is related to this donut kind of structure. Insulated state, we can think about this closed surface structure. So then also we talk about the spin orbit coupling. So that gives you this the motion happening in both directions because of the spin up and spin down. That is in Q space we are talking about electron moving in this direction, or on the bottom it's coming. So that's mostly coming from this spin orbit interaction term. Everybody should understand this one. Basically, this is the Rishba effect, right? So coming from the electric field due to the motion of your electron that causes a magnetic field, so that interacts with the magnetic moment, giving rise to this spin orbit energy. So yeah, that's all. So I'm going to stop here. So this will be the last lecture of this series. Thank you.